limit of a function. So in Unit 2, we saw that the main properties and definitions of functions and the main functions we will use throughout the course. And now, having gone in Unit 3 and 4 to sequences and series, we now want to go into differential calculus, okay? Which in the end it will lead us to understand how a function behaves in each point, and how it is growing or decreasing, things like that, right? So in order to get to that, first we need to introduce this definition, the limit of a function, okay? So the value of a function at a particular point A is just f of a, right? But sometimes we don't have a in the domain, and we want to know how the function is behaving close to that point A, even though a is not in the domain, okay? So, and also this will be very, well, not useful, but it's necessary to define what the derivative is, okay? So it's useful for other ideas in differential calculus. So the definition of the limit is this, okay? We say that the limit of a function f defined in a domain A and with values in the real line when x approaches A is L, and we denote it like this: the limit when x goes to A of f of x is L, if for every sequence x sub n contained in the domain such that x sub n is different from A for all natural numbers, and such that the limit of this sequence is A, okay, so it's approaching, the sequence is approaching A without touching it, then we have that the limit of the function when it takes values in this sequence, so the function of that sequence when n goes to infinity, the limit of that is L, right? So this is just a way, or a rigorous way to think of how to approach one particular value in the line, okay? So let me illustrate that with an example. Okay, let's take our function x squared, right? And then we have the value of x squared at x2, okay? The value is 4, we know, okay? But suppose we want to compute the limit of the function at that point, right? The limit is going to coincide with this value, and this is because x squared is a continuous function, okay? But we will see that in the next unit. Okay, so how do we formalize getting closer and closer to 2, right? So we can take a sequence x sub n, something like this: 2 plus epsilon sub n, where epsilon sub n is a sequence that's different from 0 at every point, and the limit when as n goes to infinity is of this sequence is 0, right? So as n goes to infinity, then the limit when n goes to infinity of x sub n is 2, okay? And at all points x sub n is going to be different from 2, which is what the definition ensures. And also it's contained in the domain because the domain of the squared function is the real line, right? Now we can compute f when it takes values in x sub n. It's going to be 2 plus epsilon sub n squared, or in other words 4 plus epsilon 2 times epsilon sub n plus epsilon sub n squared. Now we take the limit when n goes to infinity of f of x sub n, and this is 4 plus the limit of this, which is going to be 0, plus the limit of this, which is going to be 0. So the limit of the function is going to be 4. Okay, so you see, as you're getting to this, in a sense, the idea of computing the limit is what happens when we are getting closer. If you walk through the function, it doesn't matter if you walk from the right or from the left, okay? What is the value that you would approach, okay? Now, in this case, maybe it's a bit stupid, because you can think, well, you just need to substitute, right, the value of the function in the limit. But that's not always the case, okay? This is the case because f is a continuous function. But what happens if f is not continuous in that point? So for instance, let's take this function. F of x is x minus 1 divided by x squared minus 1, right? So the domain of this function is the values that makes x squared minus 1 equals 0, or in other words, x squared is 1, x is either plus or minus 1, right? In fact, you can rearrange this, and this is x1 minus 1 divided by x plus 1 divided by x minus 1, right? So you could say that if you could rewrite this like this, if x is different than 1, right, we can get this thing, cancel this factor out. So this is equal to 1 divided by x plus 1 when x is different than 1. And it's equal to x minus 1 divided by x squared minus 1 when x is 1. Okay? Well, actually, you know, when x is 1, it's not defined, so it's just like that. Okay? So we can say, sorry about that. We can rewrite it like this. This is 1 over x plus 1 when x is different than 1. Okay? So we have this 1 over x plus 1. This is the axis. And so this is the inverse function 1 over x, but with the x shifted to the left. Okay? So if you think about it for a second, you'll see that the vertical asymptotes will be when x is minus 1. Okay, so this does something like this. Okay, and this is minus 1. Now what happens with when x is 1, then we have a hole here. Okay, so it's actually, let's see, we have this. Okay, the function does not take any value here. Okay, what's going to happen here? What is the limit when the function addresses this? Okay, now this is kind of the answer because I'm plotting this, but you're not supposed to be able to plot this yet, right? So in other words, let me summarize. The domain of this function is the reals minus 1, 1. So the limit when x goes to 1 of f of x, okay, the limit when x goes to 1, x minus 1 divided by x squared minus 1, we don't know what that's going to be. We can't substitute, right? Because if we substitute, we get 0 divided by 0, okay? So what's going to happen here? Now the limit, just like before, we take a sequence x sub n, which is 1 plus epsilon sub n. And just like before, epsilon sub n is different from 0, and the limit when n goes to infinity of epsilon sub n is 0, right? So this fulfills the condition. Now we have f of x sub n is 1 plus epsilon sub n minus 1 divided by 1 plus epsilon sub n squared minus 1, which is epsilon sub n in the numerator, and we have 1 and 1 goes away, so we have epsilon sub n squared plus 2 times epsilon sub n. And we can divide, and we have 1 divided by epsilon sub n plus 2. Now the limit when n goes to infinity of f composed with x sub n is the limit of this, but the limit of epsilon sub n is 0, so then we have 1/2. Okay, that's going to be our limit. Okay, even though the function is not defined on this point. Okay, this is the limit of the function. Okay, now the definition of the limit that we have used says that this limit has to be fulfilled for every sequence, okay, that we use that approaches the value a, right? Now in this case, this will be valid for every sequence because every sequence x sub n that approaches 1 will have to have this kind of form, right? A form 1 plus something else that approaches 0, right? You can always decompose a sequence like that into a part that's 1 and the other part that's decreasing, right?